All right, so sometimes it's hard to actually get a free moving particle through space. So most of the time when you talk about particles or charges moving, they're trapped within a wire. So what's actually happening within a wire? So we have this current carrying wire, it's passing through a magnetic field. It should experience the same kind of forces, some kind of magnetic force, because all those electrons in the wire are moving. They're producing a magnetic field, or those magnetic fields will interact with the external magnetic field, and all the electrons will start moving in a certain direction within the wire. And when they move in that certain direction, they're stuck within the wire. So all these electrons are stuck inside this wire, and they start pushing on the top or pushing on the bottom or the sides of the wire. The whole wire itself is going to move upwards. Now, I just want to mention that the wire is not going to spin around in circles like an electron would by itself. The reason behind that is all of the electrons. So imagine you have an electron here, electron here, electron here. Imagine all these electrons were starting to spin upwards. They would hit the top of the wire before they can complete their loop. And then since they're all pushing upwards at the exact same time, the whole wire will just move upwards. It's not going to start spinning because all the electrons are pushing at all different parts along the wire at the same force. It would only start spinning if the forces were uneven, if one force was bigger than the other. So the wire would be pushed upwards because all the electrons are going to be pushed upwards as well, or downwards, left, or depending on how the field orientation is and the direction the electrons are moving. Okay, so what variables do you think will affect the size of this force? Well, we already know that this external magnetic field, so they say there was a magnetic field around here, the B should affect it. It affected the other one. The stronger the magnetic field, the stronger the force. Now, current is something else that's going to affect them. What current is, I think I mentioned it before in a previous video, is it is charge per second, so charge per time, Q over T. It's how many coulombs per second pass a single point. Because I don't talk about just individual electrons, I just worry about how much charge passes by a very specific point. It's measured in amperes, or capital A. Amperes, okay. But it's how many coulombs per second. So yeah, if I had more charge per second, which means the charge is moving faster, because it's covering the same distance, but I have more charge passing through the same point. So they're moving faster. That seems like it would increase the strength of the force because they're moving faster. That's what happened with the moving charge before. Faster charge, bigger magnetic field. Now the length of the wire, let's denote that by the letter L, is in meters. Now, if I have more wire within the magnetic field, I have more electrons within the magnetic field. And more electrons, if I have more electrons up here, all hitting the top of the wire, all the forces are going to add up together. I'm going to have a bigger force. Just makes sense. I'm going to have more electrons here. So that makes sense. If the wire was larger, I would have a bigger force. Now, one thing about this, the length of wire is only concerned with the length of wire within the magnetic field. Like I'll throw some trick questions at you sometimes where I talk about, okay, here's my magnetic field. It's in this little box here. Here's a wire, really long wire going through it. And I'd give you a couple different numbers and say, okay, this wire from here to here is 5 centimeters in length. But the magnetic field itself is only 2 centimeters or something, right? I'm only concerned about this piece of wire. That's the L there. It's what's inside the magnetic field that counts. The electrons outside, they're not experiencing forces, so they're not going to add on. They're going to add mass to the wire. That might be important later on, but they're not going to add force to the wire because only the electrons within the field will create a force if they're moving. If the wire's not moving or the current's not running through the wire, then there's no force. The angle is the same idea before. I remember the video way back a couple of videos ago. We talked about how the angle could change the force, but everything, most of the time, we're going to see is going to be perpendicular anyway. But if it's not perpendicular, you always want the perpendicular part of wire. So if my wire is not perpendicular to the field, then I'm going to have to determine what that is. Now you'd see that more the case if I had a field that looked like this. See, that's my field. It's going down. And if I had a wire kind of going this direction through the field, I'm only concerned about not how long this wire is. Like this wire could be like 10 centimeters long. I'm only concerned about this length here, the perpendicular length. That's what I want, right? This is what I want here, right? So you'd have to know some angles and stuff to do that. This parallel piece, the same logic applies with the other one. My hand rule just doesn't work. If it's parallel, I can't orient the direction of the electrons in the field in a way that they're both going the same direction, because these have to be 90 degrees to each other. So this part of the wire I don't care about. So you use some trig to find out that perpendicular piece, and then we can do the math. Now, what is the math behind this? Now we have this formula here, like it's got this I, it's got the L, it's got the B, it's got everything that we need in it. It's got the sine theta, which we don't care about because we're talking about perpendicular anyway. I won't cross it off though. I'll just leave it there. But this is at 90 degrees here. Remember, sine 90 is 1, so that doesn't really do anything. Okay, so could I just do it? Can I just go I times L times B and expect to get the same result as before? So how do these two formulas, how do they compare to each other? Because they end up being the magnetic force, so they should be essentially the same thing. So let's just look at the units here. So we got Q being C. We got meters per second, and then we got Teslas. Okay. Now, if I just slightly move around some of these units down here, the C and the M and the S, if I just move them around, I can move the S over underneath the C instead, underneath the coulombs. And then I get this. But then you notice that what I was talking about before, a current is a Q over T, which is the coulombs per second. Here we have another coulombs per second. So that this formula could change between the two. That becomes the I. This is meters, that's the length in the wire. And this is just still Tesla, so that doesn't change. So these are the same formula. We just use them in different situations. We use the bottom one when we talk about wires. We use the top one when we talk about just single charges moving through space. So, but they are essentially the same formula. They have the exact same units. Just kind of the units are just jumbled up a little bit. That's just useful to know. Okay, now this picture looks exactly the same as the previous one, like one we did before with all the imaginary magnets that we drew and how did they interact. You could see that we had the same idea. The field coming out here, so that's why that's north. The field is going in, so that's why that's south. Field's coming out, that's why that's north. Field's going in, that's why it's south. These guys are going to attract each other. And then these ones down here, the same logic. That's south, that's out, so that's in, or north, sorry. These are both like charge or like poles, so they're going to repel each other. So there's going to be a force on this wire now. There's a bunch of electrons all going in the same direction. So the wire is going to be forced upwards. These magnets, like I said before, are going to get forced downwards, but usually they're stationary. So they won't move too much, but the wire will be forced upwards. Now, the hand rule still applies, the exact same left-hand rule we had before. So current, in this course and most university courses, current is electron flow, so we use the left hand. If we talk about conventional current, we use our right hand because conventional current is the opposite direction of electron flow, so my conventional current is going to go the other way. Just because that's what convention was. They thought current was positive. Now let's load up one of these MagLab applets that I have here. So let's look at this MagLab that we have. Okay. So here's the MagLab. Okay. So I want to do let's do a little snip here. Let's create a little new snip. Okay. So here's my applet. Now a battery here, the electrons are going to flow out of the south, the negative part. So my electrons are going to flow this direction. Now, when I do this one on the lab, you're going to notice that when I turn on this thing, they'll say the current comes out the other side because they talk about conventional current. But we're going to use our left hand for all these. This is a MagLab. It's in the States, so they still use conventional current a lot in their classes, even though that is technically wrong. So let's go back to the picture here. So the electron flow, so when I close this circuit, we got this little knife switch. So this will close up the circuit, so the electrons will flow through the circuit. They'll flow through all this. They'll go up this wire over here. They'll go down here. They'll go across this piece here. That's going to be inside this magnetic field, and then complete this circuit. I'm really just worried about this piece right here. So we're going to have electron flow going that direction. Now, if I look at the north to the south here, my field is going to go this direction, from north to south. So we're going to use our hand rule here. That if I were to turn this on, which way would the electron, or which way would the wire be forced? So north to south, so that's going upwards. My electron is going kind of this direction. It looks like it's going into the page a little bit based on the three-dimensional picture. So my palm is right here. My palm is forced this direction. Okay? So it's going to go out in that direction towards the battery. So it looks like there's going to be a force here. We have green on the picture already. Let's go black here. We're going to have a force this direction. So if I did this, and I turn this on, the wire would be deflected in towards, it's not going to be deflected all the way out because gravity is going to kind of pull it back down a little bit because it has mass. So if I hit the switch, yeah, so it gets pulled in. You notice that the direction of the current's going the other way because they're using conventional current. Technically, you just use your right hand to do that then. Just use it. It'd end up being the exact same. So it'd be going, if I were to try to do that again, there it would look like that. And you still have the same force as this one. Okay. You can look at some of these things too. Like if I treat that, you can see the wires. You can see that circular magnetic field here. You could put in the little mini magnets around here. You could put your mini magnets on the side here and see how they were to be attracted or repelled. There's my field lines from north to south. If I flip the magnet, it should go the other way because my field lines change direction. If I flip the battery, it should also go the other way because my currents flow going in a different direction too. Okay. Nope. Now, like I was saying before, like we just did, we can determine the direction by using the third hand rule again, the third left hand rule. The thumb is still the direction of the electron flow. The fingers is still the magnetic field. The palm is still the force. So you can see on this is just a description of exactly what I said before. Oh, sorry about that. Let me just get the right view here. Now, I already talked about this already, but a Tesla, the magnetic field strength is a Tesla. You can just put it on this slide as well. It's denoted by newtons per. And if I do it by this way, because remember we did the last one where we had force divided by Q and V. If I did that one, I get newtons per coulomb meters, and the second flips up, so I get newton seconds per coulomb meter. Let's see if it works the same way on this one. So we got current, which is a coulomb per second. There's a meter. Second flips up to the top. Yeah, I get the same thing, a newton second per coulomb meter. And this is a Tesla, a capital T. Yeah. Should probably put some vector arrows on there. Okay. All right, here's the same thing. They use amps in this one, but I changed it to a coulomb per second, just so I can see that they match the previous formula as well. You can read what a Tesla actually stands for. It's the strength of the magnetic field is defined. The strength of the magnetic field, is defined as the force acting on a 1 meter long wire and a 1 amp of current. Now, usually you don't have a meter of wire. and 1 amp of current is quite large, it's quite dangerous actually. So it's more theoretical than anything, because you usually have a much smaller wire and much smaller currents. So you probably won't have that much of a Tesla. Like 1 Tesla is actually quite large. You usually have milliteslas or microteslas. I think the largest man-made one is like 5 Teslas. And that can literally hold a chair perpendicular to the magnet. So let's say I had a magnet right here, and then I had a chair attached to a wire. It would almost hold it perpendicular to the ground. It's quite strong. So we're going to stop the video at this point here. And then we have a few example questions on the next pages here. We also have another video here. We have to watch this video, and I also have another one of those MagLab descriptions. We'll watch those on the next. We'll do those on the next part of this lesson. Okay, I'll see you later.